Hello, everyone. Last time we discussed or we started our series of discussions about mathematical physics. We discussed there the Fredholm integral equation and the Volterra integral equation. So today I decided to shift our discussions to a series of tutorials about the problems in vector calculus. So suppose we are asked to prove if phi is equal to 1 over r, where r is the magnitude of the position vector given by the square root of x squared plus y squared plus z squared, then the gradient of phi equals negative r over r cubed, or negative r times r to the negative 3. Now to prove this one, we have to consider the fact, or we have to note that the gradient operator is given by this equation. This is partial with respect to x of I hat plus partial with respect to y j hat plus partial with respect to z k hat. And then we're going to operate this one to r phi and see if the problem could be proved by this. Okay, so we have to operate this gradient operator to r phi. So we have partial with respect to x I hat plus partial with respect to y j hat plus partial with respect to z k hat, okay, times phi. This is actually r phi because as we know, okay, r phi in the previous slide is given by 1 over r. Okay, so as we know, r equals x squared plus y squared plus z squared to the 1/2. Now since this is 1 over r, so basically, okay, we have to change the sign in the exponent. So we have the gradient of phi is equal to these quantities. And then eventually we're going to distribute this one. We have partial with respect to x I hat of r phi. We have partial with respect to y j hat of r phi, and then we have partial with respect to z of r phi. Okay, so after distributing this one, okay, we have these following results. Now we have partial with respect to x of x squared plus y squared plus z squared to the negative 1/2 I hat. We have partial with respect to y of x squared plus y squared plus z squared to the negative 1/2 j hat plus partial with respect to z of x squared plus y squared plus z squared to the negative 1/2 k hat. And of course, we have to get the derivative, no, or the partial of this phi. And so for this first term, we have to bring down, or we have to take negative 1/2. Okay, so we have negative 1/2 times the derivative of x squared, so we have 2x. Okay, times x squared plus y squared plus z squared raised to the negative 3/2, because obviously when we take or when we took negative 1/2, what's remaining is negative 3/2 I hat. So this is for the first term. For the second term, we do the same. Only that in this case, now we have to take the derivative of y squared. So we have 2y. Okay, the same, we have x squared plus y squared plus z squared to the negative 3/2 j hat minus, we do the same for the third term. We have minus 1/2 2z because we have to get the derivative of z squared times x squared plus y squared plus z squared raised to the negative 3/2 k hat. And as we can notice now, this x squared plus y squared plus z squared raised to the negative 3/2 is actually common. So we can just factor this out of the equation, or factor this out. And we also can notice that 2 could be cancelled out. Okay, so we cancel out 2. We cancel out 2. And obviously, we can see that what's remaining is negative x I hat minus y j hat minus z k hat, and then the factor, which is x squared plus y squared plus z squared to the negative 3/2. So this is the remaining. Now, of course, we factor this out because this is common for the three terms. So therefore, the gradient of phi, it has been proven now, is equal to negative r to the negative 3, or negative r times r to the negative 3. And if you are curious, the reason is because this is actually r, or our position vector, and then this is, okay, this is r to the negative 3. Okay, so I guess that's all. If you have some questions or clarifications, you may type your comments or questions in the comment section provided. Thank you.